Okay, good evening, everybody. I'd like to introduce William to you all. William is a structural engineer with 20 years international experience in the UK, Hong Kong, Australia, and Canada. He moved to Vancouver and joined FastNet in 2015, and following many years at the Hong Kong office of Arrow. His career has focused on bringing together twin passions of structurally expressive building projects and fundamental technical research and development. Being based on the West Coast, he has a particular interest in seismic design and performance of buildings. William is currently Director of Design at FastNet, while also maintaining a role as engineer of record on many of the firm's larger building projects. His notable projects include restoration of the Central Police Station compound in Hong Kong, the expansion of the National Arts Centre in Ottawa, the new Ottawa Public Library, and the new Vancouver Art Gallery. He is a chartered structural and civil engineer in both UK and Hong Kong, and designated structural engineer in Canada. In 2013, he was awarded the Innovation Grand Prize by the Hong Kong Institution of Engineers for his work on historical structures in Hong Kong. He currently sits on the Seismic and Dynamic Events panel at the Institution of Structural Engineers in the UK. William has a degree in engineering science from Oxford University and a master's degree in structural engineering from the University of Hong Kong. Would you please welcome William to this presentation? Thank you.
Thanks, Hugh.
Okay, I will turn it over to you, William. Thank you.
Thank you. Can you hear me?
Yep, we can hear you.
Great, thanks. It's always good for someone to reply. Thank you very much for the introduction, Hugh, and also the opportunity to speak to this group. We do have a similar group on the West Coast, but I confess with these evening affairs and young kids at home, I don't really attend those as much as I probably should. So I'm glad to see that this exists in the prairies as well. I've, as Hugh said, I've been in Canada since 2015 in Vancouver during that time. I've been working mainly in Vancouver, but also quite a bit in Ottawa. And I visited Edmonton a few times. We have an office there as well. So it's a nice part of the country. I'm assuming I'm talking to a sort of a mixture of different chartered engineers, and my specialism is obviously structures and building structures. This talk is fairly technical because a lot of engineers like to just listen to technical content. I hope it's not too specific for the variety of engineers that are listening today, but I hope it's enjoyable. The title of this talk, Earthquake Resistant Buildings and Recent Experiences, is a little bit cheeky, a little bit unjustifiably reassuring, as we'll see in some of the pictures, and as obviously people have seen in the recent devastation of several earthquakes, that an earthquake resistant building is fairly hard to come by. I guess finally I should say on my background that I've had the last 8 years here in Canada, where seismic design is what I do pretty much every day. Living on the West Coast. Before that, most of my work was in Hong Kong and on obviously in a typhoon region with everything dominated by winds. There's a very different perspective you take to design, going between those two different types of loading, and I imagine in the prairies that it's seismic design of buildings is not the top thing that you work on in your day to day. Anyway, I'll get straight into this. Get my slides to move. Here we go. So I've presentation's a bit of a compilation of other material I've put together. I'm hoping this will be 45 minutes to an hour, and we'll see how it goes. This came to me through the seismic and dynamic events panel, the iStruct. I think that's where you reached out to. So I'll just talk a little bit about what that is. It was also, I think, in response to the earthquake earlier this year in Turkey that sparked a bit of an interest in what we're doing here in Canada. So some observations from the Turkey earthquake and other notable earthquakes before that, not at great length, but some observations. And then a bit of a sort of summary of how we go about things in Canada, what our basic standards are and what are some of the limitations. And then some more juicy bits on newer technologies and how we can actually do better with some case studies of some of our work here in Vancouver. Closing up with some general reflections at the end. The iStruct has many panels. One of them is called the Seismic and Dynamic Events panel. I joined 2 years ago. There was a year where not much happened with the, I think, a change of chairman and a bit of confusion about who's doing what. But the last year we've been meeting up regularly, and it's a sort of enjoyable gathering of seismic engineers and people working on other dynamic problems, not just earthquakes, from all around the world. And it's been really nice to have that opportunity to engage with people in Asia and New Zealand and other seismic parts of Europe, as well as obviously in the UK. The remit is, as far as I can tell, to sort of provide access to resources for members and organizations that are affiliated with the iStruct, to write articles and posts and guidance documents about seismic and dynamic events, develop training for members, and then sort of collaborate with the external seismic community, some of the other organizations that are interested in earthquakes and seismic design. So to begin with, some observations from Turkey and other recent earthquakes. I've seen this as a normal engineer working on earthquakes and seeing what I've read in the reports. I haven't been out there myself, so this is all my perspective from Canada. And Turkey was obviously this year, but there were several other notable earthquakes from the previous decade, which all hit the news both widely and within the engineering community. Christchurch and the Japan earthquake in 2011, and a year before that, the Haiti and Chile earthquakes, all to varying degrees, causing some amount of devastation, with lessons to be learned from them. I have quite a few slides here on Turkey and fewer on the others, because I don't want to dwell the whole presentation on this. Some understanding of the level of the Turkey earthquake, and these are 3 different stations. The red line there is the 2475 year earthquake, which is what it's the same as the design level or the design frequency that we designed to in Canada. And you can see that some of these stations where these measurements were taken at some periods, accelerations recorded well over that spectrum. In other locations and other periods, levels below that hazard spectrum. There was an enormous number, as it was obvious to everyone seeing it on the news, of buildings that were damaged or collapsed. 60,000. Many of them built before the 2000s, but a number you can't ignore built after the 2000s. And typical buildings at risk were concrete moment frames, particularly with soft stories, which we'll get into, and other construction deficiencies. Example here of a 12-story reinforced concrete shear wall building, and some potential features that may have contributed to collapse were a very wide shear wall, and insufficient shear wall and foundation connections in the shorter direction, and again a soft story effect on the first floor. Some examples from some of these stations where you can see the hazard spectrum. In this location, the response spectrum at periods of above 1 second, which is probably where these buildings were, was at the design spectrum. So generally, just to say, some pretty high hazard levels. In Haiti, the spectrum was well above. Sorry, the hazard was well above the spectrum, and you can see from the image that speaks for itself what happened there. Summary of some other findings. 24 buildings of more than 20,000 for education purposes collapsed. 83 reported as heavily damaged. 15 hospitals with partial heavy damage and 2 completely destroyed. I've worked on hospitals in Canada and used references from Turkey actually that where they do base isolate some of their hospitals. So by no means were the standards that should be being followed deficient in Turkey. Enormous numbers of people who've lost their homes, and we'll get onto that sort of discussion about resilience later, and damage to infrastructure, to the airport and water supply and sewage removal, which again comes into the discussion of it not being just about buildings. After an earthquake, there's all the associated infrastructure that is just as vital. On Christchurch, just a couple of small slides, again, because the story of Christchurch is familiar to everyone. This was an image directly after the earthquake, and the buildings basically did the job they were asked to do by the code. They didn't collapse. They allowed people to evacuate. And the highlighted building there reappears in the later photo, but this was a typical image from inside the building. So you can see, despite meeting their code expectations, they are not usable and require extensive repairs if you want to reuse them. And then I think this photo was a year or two afterwards. You can see the circle building is still there as a reference point in the picture, but very little else. And this was due to decisions made by owners that there was no economical sense in retaining the buildings and trying to repair them, and they were all demolished. And that's, obviously clear what the effect on the business community is. This slide should have been combined. This is one of these ones where things pop up later, but the buildings with the X's were subsequently demolished as well. So general observations on these earthquakes, and some of these apply to the Japan and Haiti and Chile earthquakes as well, that the damage affects more than just buildings, and resilience depends on more than just structures. So the damage to infrastructure and the airports in Turkey and the hospitals is just as important as individual buildings. Secondly, the performance provided by modern codes is often not aligned with public expectations, and hence the misleading or cheeky title of this presentation that the public expectation is often that we design earthquake-proof buildings, which is not what not what the code asks us to design. For Turkey and possibly in Haiti, less so in Japan and Chile, neglect in in construction or regulations being lax does lead to poor performance and collapse. And that's something we don't see really so much in Canada, where we do have tighter control on what happens during construction. Japan obviously has a widespread implementation of isolated buildings. And if technology allows, you'll see a video of one of them during the Japan earthquake later on, which allowed continued functionality of those facilities. And it does raise the question of why we don't do more of that, certainly outside Japan. And then obviously from the New Zealand example, the cost of repair and business disruption, decisions to demolish based not on necessity of or impracticality of repairing, but cost of repairing and a sense that the whole region or the whole area is emptying, and it makes no economic sense to repair a building. There were just brief observations from those earthquakes before we come closer to home and discuss Canada and some of the work we're doing here. So this will be a bit of an overview of how we're designing buildings in Canada. I just want to go through seismicity levels, historical code development. I thought may be interesting. The measures we have in design to control performance, and then performance expectations and limitations. This is from NRCan, just a nice colorful map of historical earthquakes. And so clearly on the West Coast, we see very intense earthquakes, at least in the codes. Different, similar in intensity in the codes to the West Coast of the US, but rather different in that we don't experience them day to day on the West Coast. Even I've been here 8 years and I've felt one minor tremor, which contrasts quite a lot with California, for example, where the public will have experienced what an earthquake is, and it's real to them. The other area of the country with moderate to large earthquakes, not as big as the West Coast, is around the Ottawa region and the St. Lawrence River in Quebec. There's sort of 2/3 of the intensity we get on the West Coast. On the West Coast, we're all sitting here waiting for what they call the big one, which is a subduction earthquake, which is apparently supposed to happen every 300 years, and the last one was 323 years ago. So sometimes fills some of us with a bit of trepidation. That's the very, very rare, very, very large, very long duration earthquake that is predicted and is now incorporated in our codes, but is obviously hard to work out what to design for something that's so rare but so powerful. The two other sources of earthquakes are the deep earthquakes and the crustal earthquakes that are more frequent but less severe. Historically, I think this probably varies what happens in the US, but I don't know the history of the US codes as well. But 1941 was when some amount of seismic consideration came into the NVC, and then there's a series of developments as the codes got more refined. People started to understand more about behavior of buildings and earthquakes. And across the years, you can see seismic zones got brought in, meaning different parts of the country, designed to different levels, stiffness effects, different periods of buildings respond differently. Importance factors, so some buildings are more important than others. Soil factors, where you build on the ground, affects how much acceleration you feel. And then a sort of a 1970 being a key date where probabilistic analysis was brought in to try to be a bit more mathematical basis to it than being purely deterministic at a 100-year hazard level. And then with the advent of computer analysis, dynamic analysis started to come in. In 85, the hazard level was updated to a 475-year hazard, and at this point the load factors, you adopt that 475 hazard as it is without factoring it up in the same way as you do for other loading. 1990 was the other sort of milestone year when we think of buildings where ductile detailing was really developed to a much greater degree, and post 1990 buildings you can feel more comfortable in. Pre 1990 buildings of certain types, you may be less comfortable about the behavior in an earthquake. And then there's a succession of codes leading up to today with the hazard redefined at the 2475-year level and more definition of the irregularities. All of this is making it more of a specialism to design for earthquakes, and you can ponder on the increased specialism at losing, whether we lose sight of the forest because we're concentrating on the trees and working our way through some extremely complex processes now. And then finally, where we are right now today is using some performance-based design where we need to, or where we want to prove something in particular, but it's not a full requirement, and the future may be that performance-based codes become more of they become codes, they become a requirement. So for building design, the levers we have and the constraints around us, the control measures, there are definitions of irregularities, such as a weak story, which is the photo on the right, where you have a story lower down that's not as strong as stories above it, which is a prime cause of collapse. Discontinuities where shear walls or brace bays step around as they go down the building. Geometric irregularities, funky shapes. Torsion, also related with funky shapes, where your resistance is off center. And gravity-induced lateral demand, where you have either sort of an inclined column or large cantilevers that are in the motion of the earthquake. The building slowly ratchets over to one side because there's some gravity naturally pulling it to one side or the other. We have to deal with more important buildings, hospitals and such. We just increase the forces and we design them to deflect less, to have smaller drift limits. But there's still quite a lot you can do within these constraints, and they don't force you into perfectly regular buildings with ideal seismic performance. So the performance expectations are simply for a normal importance building, life safety. Basically what you saw in the photos of Christchurch immediately after the earthquake, buildings still standing, people coming out. People can go back in to repair them with due care, and mostly not collapsing. And for higher importance buildings, you get better performance, but there's no explicit guarantee of functionality or being able to reoccupy those buildings. And an image on the right there of I say typical, but a possible, not unrealistic amount of damage from a code compliant building in a code level earthquake. So there's limitations to this framework. Between a whole load of code compliant buildings, you can have a large variation in what the actual performance is. You can comply with all those limitations on irregularities and the different methods that pushes you through in the code, and some buildings will be better than others. Some effects that I don't see being how they're implemented in the codes. I think they're taken into account in some way, but long duration earthquake effects, that's the big one we have on the West Coast, which, you know, supposedly could last for minutes, 10 minutes even. How well that's understood, I don't know. The effect of aftershocks, you know, the code asks you to design for an earthquake of this size. If another one comes along and another one comes along afterwards, you're applying that to a damaged building. And then getting on to after the earthquake, damage and time or cost to repair is not discussed by the codes, nor is whether it's able to function. So with that sort of brief overview, I wanted to give some examples of newer technologies and some ways we can do things better. So I've got two case studies, one in more depth than the other, of a low damage seismic system using seismic friction joints. This picture on the screen is from one of those case studies. So this is one way we can improve our performance. After that, I wanted to talk about isolation systems, some benefits and considerations based on quite a well-developed feasibility study we did do in Canada, but didn't get implemented in the end. And thirdly, improving our understanding through assessments of post-earthquake functionality and how we can do that, which again is also happening on a couple of projects I'm working on at the moment. So the first one here on seismic friction joints. This is a current project in Vancouver on Keith Drive in the main city of Vancouver. It's currently this is obviously a rendering. It's under construction at the moment, and I think it's out of the ground, but the structure's not yet finished. So it's this sort of, what you see here is more of an architectural external honeycomb shape, but behind that shape is a series of braced bays. On plan, this is a mass timber building, so it's mass timber columns on glulam beams and CLT panels, and east-west direction timber braced bays, north-south a mixture of braced bays and CLT shear walls. My involvement in this building was pretty much on the consulting on the nonlinear analysis rather than the sort of general design of the building. But it's a fairly straightforward layout, which is when I was commenting on the variation of performance you can get within different types of code compliant buildings, having balance in the distribution of lateral systems intrinsically, leads to better seismic performance. Here we've got nicely balanced brace bays on each side, and these CLT shear walls nicely spread across the length in the shorter direction. Yes, which is shown on the slide here. an elevation here, so very simple, a concrete basement, and then once you're at the ground, top to bottom, uniform, consistent bracing. And these are the CLT shear walls. So whether wood as the lateral system is a reasonable way to go, it does start to get stretched with the height you go to. This was a 10-story building, and you can start to see the amount of steel you need to put in to connect all the bits of wood together. So this was stretching the height limit. In fact, it went beyond the code on the height limit for a wood lateral system. So we had to do performance-based design and a peer review process. This was also a project where the design team wanted to explore a new technology for creating a more ductile and resilient lateral system. And we basically researched an idea, completed research on it, found that it probably would not meet the performance requirements we really wanted. And then I'll show you where we went to afterwards. But the idea here was to get energy dissipation through yielding of steel in a fairly cheap and easily reproducible way. So this is you can see in the photo, the sort of steel plates there with that diamond, or that triangle cut out, and the series of holes where one side is connected to the base and the other side of the holes is connected to the bracing member. And a drawing here of a typical node. So I'll go back to this one, but so as the brace extends, the steel that's between those holes starts to shear and yield back and forwards, back and forwards, back and forwards. You can get an understanding of forces, you can design the amount of steel between the holes, but you really need to do some testing to work out how far that goes and what its elongation and fracture would be. So we drew up a set of details for this. We ran a testing program, mostly at the University of Alberta, but also at Queen's, and did some. This was literature review beforehand, showing some previous research that had been done on this concept, and you can see that sort of shearing of steel between the holes. So this was the basis of thinking this may be feasible. But the key to this is reaching your force level, but also being able to continue when the earthquake is larger than you think, and be able to cycle through repeated motions. The design variables we had were the number of holes sort of vertically on the page, and the number of holes, the number of rows of them, and you can tune your deformation capacity with the number of rows, and you can tune the strength with the length of that column up and down the page. So all this seemed like a good idea, and that concept was plausible and real. The loading tests, though, showed that they met what we wanted for strength requirement, and they deformed enough. But you can see after they got to some deformation, the load dropped off very sharply. So with all the uncertainties that come into knowing what a real earthquake may be, you saw from the Turkey ones, and how a building actually does perform in a real earthquake, you want to have something that can continue, even if it's not getting stronger, but continue to deform for a much greater length. So we still continued with some research on this topic, but we didn't implement it on this project after that. Instead, we went to Tectonus, which is a company from New Zealand who have produced these slip friction joints. So these are these two pieces of orange steel that you can see in the diagram there, clamped between the blue steel, the black steel plates with sprung bolts to hold it all together. And as the ends attached to the orange pieces pull outwards and push inwards, they slide across the black and dissipate their energy through heat. There's been an enormous amount of testing done by the manufacturers, by Tectonus, on these. So they came with all the reliability we needed. So this is the first video, which will have a test, see if this works, of Tectonus being tested. And I'll let you watch it, but you can just see how you get the idea of how it works with those orange plates pulling apart from each other. You can also see the hysteresis curve there with a sort of classic flag shape to it. So the the nonlinear analysis to do this, essentially, you open an ETABS model and use a nonlinear joint. All the research that has to happen goes into defining the various points on the hysteresis curve. This is an image not from this project, but I think possibly from Tectonus themselves, of these joints in a real building. And so we updated all our details to incorporate these frames, and including in the brace bays and the CLT panels here. So here the gravity comes down both ends and through a central pin in the middle. The pin obviously allows the wall to rotate such that the motion is only causing extension and compression of these friction joints, and all the energy has to come out of there. The shear on the CLT wall then goes out through that pin in the middle, and all that goes down onto concrete, which is over-designed to remain fully elastic and not undergo any damage. And that's it. This is a rendering of the final building, but it should be completed fairly soon. It's under construction at the moment. The second sort of case study was using the same joints, and it's the building I'm in at the moment, which is our office, which is complete. So I'm sitting in this building at the moment. This is also a mass timber building. You see it's a shorter building with steel columns, CLT panels on glulam beams. The glulam beams just run in the short direction across the whole 12-meter width of the building. Very simple, regular layout. Knife plates from the steel columns into the glulam beams. It's an image there from construction. We did quite a lot of vibration testing as well on this building to understand mass timber vibration performance. And a sort of during construction image there. And we wanted to integrate some element of seismic resistance in this building. It's not fully operational in both directions, but you can see on the shorter direction, we've got 4 or 5 pairs of Tectonus joints incorporated in the building, and that's one of them during construction, and in our stairwell at the moment as we go up and down the stairs. We walk past these every day, which is a nice pieces of exposed structure for structural engineers to walk past every day. So that was sort of two real case studies on low damage technology, not zero damage, but at least low damage, and elements that can be replaced after an earthquake if they do get damaged. The best you can ever get with low damage or minimal damage is obviously isolating your building from an earthquake. So this was the second discussion I wanted to have here, to talk about some of the benefits and considerations. As I said earlier, this is based on a very very completely developed scheme that we did for a project, which didn't eventually get implemented, but was very instructive as to how you would go about implementing a base isolated building. To my knowledge, there is one school retrofit in Canada, in Vancouver, that's been isolated, and there's all the work that's going on the Parliament buildings at the moment, which I believe involves base isolation. But other than that, we lag well behind, certainly Japan in the lead, but also the US with implementing isolation systems. But this is what it looks like in some bigger buildings. This and the following photos are from San Francisco. So very large isolators holding up the whole building above it, and then this is obviously in the basement, going down to foundations. Close up of one of these isolators, and there are two main types: the lead core rubber dampers, and what we were looking at in our projects, which is friction. In fact, the triple friction pendulum dampers, which are two concave, highly polished steel surfaces with a bearing in the middle, and in fact, two layers of sliding on each side. That versus the normal friction pendulum, it just gives you a different shape of your curve, hysteresis curve, when you plot displacement against force. Some of the considerations are that you have to allow a building to slide around. So at some point you have to cross that gap, and you need to have a moat that you can walk across, and anything going in and out of the building has to be able to be flexible. So this is from San Francisco General Hospital. You can see the flexible utility connections on the left, and you can see the moat construction on the right. In San Francisco and in California, the size of these moats is larger than we need in Vancouver, just given the higher seismicity down there. For a Vancouver example, this could be 2 feet wide or 3 feet wide, but it's certainly a large consideration in the design, and in terms of providing access to utilities going in and out of the building. A few slides on how this all works, but I'm sure you may have seen versions of these slides elsewhere. For a conventional structure, it has to move with the earthquake, and damage occurs up the height of the building. With a isolated structure, all the displacement happens. It's confined to those isolators that are designed to displace without any damage. Viewing this on a spectrum, this means you sort of slide down that hazard curve to a lower intensity at a longer period. The next few slides will be the most sort of technical, analytical ones, so feel free to glaze over a little bit if you need to. But this is the Vancouver spectrum converted into a acceleration displacement spectrum rather than a acceleration period spectrum. So the period on this graph is the radial lines that come out of the origin. So I've taken a typical 1 second building and drawn on what happens when you do a normal fixed base design. You get your position on the spectrum up there at 1 second in the circle, and that's showing 0.4 something G. So I mean, you get sort of 45% base shear. You then say, well, the building is just going to damage itself as it sways around, and through all that energy dissipation and plastic motion, you don't need to design the building for more than some factor less than that. I've taken the example of a RDRO of 2.8 building. So you design for 1/3 of that 45%. You then say, well, the deflections are still big. They just go inelastic, even if you're not designing for the full force. So you slide across horizontally to the final solid blue dot on the screen there. So you end up with a base shear of 15%, and you've undergone a lot of damage in that process of going down from 45%. The isolated building, you slide down the curve. The standard spectrum is the 5% damp spectrum, so you slide down that with no damage at all. In doing so, your period increases. And then, depending on what you've got as an isolator, there's, in what we looked at with the friction pendulum isolators, they dissipate energy through friction, and they actually provide, in addition to accommodating all the deflection, all the displacement, they provide damping. So you then slide inwards along that radial period line to some point where the amount of damping provided by the isolator matches the reduced spectrum at a higher damping level. So the multicolors here are the design spectrum at higher damping levels, and then you layer onto that the performance, the hysteresis curve of your actual product. The black line here, and where they meet is your working point. So for this example here, we got a base shear of 7.5%. So half of the base shear you got to design the building for the fixed base. But not only that, you've got that without undergoing any damage, which is the main attraction to this. It's not just that your walls may be thinner, but it's that they don't get damaged in the earthquake. So a real example of this, which is sort of here to illustrate the importance of the question of why we don't do this more, was the Japan earthquake. So it was magnitude 9 or 9 point something. The most powerful earthquake ever recorded in Japan. Shook for 3 minutes, which is a long time to be subjected to shaking. 3,000 people died across the city, 16,000 across the country. More than 100,000 buildings totally collapsed. This example is from a base isolated hospital, 5 stories, 4,000 people in the hospital over the 7 days after the earthquake. No staff injured, no damage to medical equipment, and no broken windows or collapsed ceilings. I mean, this is the articles we've been reading. Presumably that's the case, and not exaggerated, but you can get the sense, even if there was some minor damage, that's fairly phenomenal performance. This is a long video, but at least to watch just the first little bit of it to give you a sense of what the people experience when the earthquake happens. And I'll stop talking while it plays for a little bit, but just have a look at how little is going on in the hospital. It's 13 minutes, so I'll just play it for a little bit. I'll pause that there. You can see it's on YouTube, so feel free to go and have a look. But clearly, this is the type of hospital you would want up and running following a major earthquake. So, talking a bit about some of the the details of why you want to do this. There's the obvious generally obvious why you'd want that kind of performance, but also the implications and the costs. On the benefit side, you get vastly decreased damage. The only economical way to achieve full functionality after a major earthquake, the only way to economically to be resistant to an earthquake, reduced financial loss and downtime. Not necessarily zero, but vastly reduced. Reduced seismic load in non-structural components and the damage associated with that, and no reduction in structural capacity to resist aftershocks or future earthquakes. The implications, the most obvious one, are the cost of doing this, and in our study, we'd read about numbers of 2 to 3%. We found it may even be substantially less than that, closer to half or 1%. We didn't go through with this full design, but the design process itself becomes fairly arduous. You have to do performance-based seismic design and have an independent peer review process to ensure that's done correctly. And then you need to design a moat around the building and flexible connections. But I certainly feel like this should be the norm for what we do with post-disaster buildings. And I'll reflect a bit at the end on what the challenges are to moving more in that direction. So my final piece before getting to a sort of closing is not on the technology itself, but about understanding how buildings do perform other than meeting code requirements after an earthquake. And we've got two buildings, two hospitals in Vancouver. We are where we have specified post-earthquake functionality assessment to happen. I'll go through a little bit of what that means. That there is a Canadian code which talks about different performance objectives. It's a little bit vague to me when I look at it, but it does give you some language to start talking about life safety, limited functionality, and full functionality. But to try to understand how a building actually behaves, as a structural engineer, we look at the structural response, and that means the drift and the accelerations. you then need to convert that into damage. So you need a way of understanding how drift and acceleration cause damage in a structural system, in non-structural components and building contents. And then when you know the damage, all with a certain probability, you need a way of understanding what does that mean for downtime and financial loss. After that, you also need to understand how downtime or partial downtime in bits of your building affects the functionality of your building. So the tool we've used is the FEMA P58 document and accompanying sort of software. There's free version called PACT and a proprietary version called SB3, and we've used both. This is a method that allows you to estimate the cost to repair and the time to repair. It does actually output quite a few other parameters, but we've just started with those two basic ones. It also, I think, talks about environmental cost and predicted probability of getting a red placard after an event, and one other thing. To implement this on a design is quite interesting. It's not obvious how to go about it because it's something that you need to know a lot of the details of all the components and the non-structural components in the building. A lot of things that may not be known until you get to the construction and the trades come on board. So it's not something that you deal with in isolation in the structure. So there are two ways of doing it. One is that it's a collaborative effort with the client in a non-binding arrangement as you go through the design, and then as you get into the detailed design and even the construction stage when trades are on board, you fully understand the building and you learn how it will perform. But by that stage, you can't do anything about it. You just get that understanding. The other way to go about it is to say that there have to be some targets. So essentially, this is without target approach or a with target approach, and we've done it in both cases with the targets, contractually required targets, which comes with problems in terms of the process, which we've had to sort of work through. Because the design is not fully known at the time at which you need to finish specifying the structure. But so anyway, some of the specification considerations that you need to think about are what is the target reasonable cost of repair as a percentage of replacement cost? What should be a reasonable target time to repair the building? Should you be considering that for a frequent earthquake or a medium earthquake or a rare earthquake? Should you be looking at median results across earthquakes or extreme values? And then all the assumptions that go into calculating how long it takes to repair a building. Does this happen floor by floor, or does it happen everything happens at once? The great thing is that the FEMA P58 document takes you through that process and choosing these variables, and it gives a lot of very typical results for what percentage of replacement costs you may need to pay to repair it, and what a typical repair time may be for different types of buildings and importance categories of buildings. So it does give you a baseline. Once you do know damage, or at least you have this probabilistic estimate of damage, then the really interesting bit, which is I don't think is fully happened in Canada, and we're sort of scratching the surface here, is how you get an understanding of functionality once you know that a shear wall is cracked or an elevator is stopped. or some equipment isn't working for X number of days. And there's some researchers have been looking into this. This was just an image here I found from a researcher a few years ago on a sort of process for looking at damage. And then the key thing there is that square that says operability, and how does function of your facility depend on all the bits and pieces that are supposed to be functioning in it. And so clearly this is something that becomes a multi-party assessment. You need involvement of the client and the other not structural engineers, the mechanical engineers and other disciplines to inform it. This is something we want to be pushing forward. But it's hard to get this type of thing to happen. So I'll just close. I think I've probably run over a fair bit, or pretty much on the hour, but some reflections, you know, from a structural engineer on building projects, at least, that we want to be heading to resilience, earthquake resilience, rather than earthquake resistance. Earthquake resistance implies that you're there doing your best to stop the earthquake happening, but you really want to be letting your building go with the flow in a way that limits damage as much as possible. The challenges to doing that, I think, are threefold. The technology, you know, like the system we've got in our building here, and the other building we're currently constructing at the moment, that technology exists, and there's lots of clever people producing more and more of it, and that doesn't seem to be the biggest challenge. Practice is, what I mean by that is people like me and structural engineers learning how to use the technology is the next biggest challenge, and the training that goes with it, both for the practitioner, but also for the checkers. And thirdly, the policy. And this is the really challenging piece, in my mind, is getting this to happen on a building. You need policy at the municipal level or provincial level to set requirements that this happens. And that involves us coming outside of the engineering community and talking with the policymakers. We've had some discussions with people in the city of Vancouver, but it requires thought on you know, how do you go about affecting policy. And on the private side, we've proposed you know, variations of systems up to private developers, and it's very hard to persuade someone to pay money when they don't have to for the code, despite the, you know, everything you can say about future payoffs in a future earthquake. Those are the ways I sort of think about the challenges in those three pieces, and then I reflect on the design choices I have to make in my day-to-day work, and where that leaves you know, me thinking about professional and ethical responsibility. You know, some examples: choosing a low damage system. There you have different choices of structural systems, and some are more expensive than others. And how much, when you work for a client, can you make that choice if there are a variety of choices that work in the code? And similarly, when you work with architects on buildings with irregular shapes, and they are all code compliant, you can make something work. But how far should you let that go when the actual performance of the building won't be as resilient? Less so on earthquakes here, but limiting material waste on the environmental side is something that now is part of our work as well. Where at what point do we put our foot down and say that's wasteful, and we're not going to design it. Versus saying our responsibility ends at making sure something is safe. I think that's where I ended with my slides. So apologies for going a bit over. As I said, this was a compilation of quite a few different things, and I wasn't quite sure how long that would take, but I hope parts of it were enjoyable and it didn't go into too much excruciating technical detail. So thank you.
Well, William, thank you very much indeed. Really incredibly interesting subject, and covered it very comprehensive manner for us. So with that, I'd like to open it for questions and answers. If people could be brief with the questions, and maybe I see there's 23 people online and about 21 people here. So we'll try and alternate a little bit. And the first question, I believe, was from Ben Yollis, saying, what is the importance of the height of the buildings? Is that a key factor?
Yeah, that's a good question. Tall or short both have different benefits. The very tall buildings, at least for us in Canada, and I think probably everywhere, with very long periods, will attract much smaller earthquake loads, versus the shorter buildings. So in easier to meet code requirements. The short buildings attract much higher relative base shear, but I think there's a mid-level building where you face the most damage. The very short buildings, which are often timber frame, residential with a lot of inherent ductility, you can feel quite happy about, is where you get to the slightly taller buildings that are still short enough to attract very heavy loads, but you've gone to concrete or masonry materials, and you start to get layouts with the classic soft story at the ground level, and where in historical standards the detailing, particularly in concrete and steel, wasn't as ductile. I think if you're using the modern codes now, those any height of building you can design to be ductile, but isolated buildings are not going to be useful above a certain height, for example. They're more for the maybe up to 10-story buildings.
Thank you, William. I'm just looking around here. I've got one question from Paul. If you could speak loudly. Sure. Can you hear me? Hey, William? Yeah.
Yeah.
I'm wondering, is there ever much consideration as to, you might be designing your building to base, but the buildings next door not designed to a base. Is that ever considered?
I caught bits of that. I think it's to do with you can design your own building to certain standards, but the building next door may not be. That's a very good point. I think about that as much in terms of infrastructure as neighboring buildings. That there's not much. What's the point of your own building being standing there fully functional if the surrounding ones are not? I mean, we have we have to limit separation of buildings for seismic movements to at least avoid pounding. But the more global effect on your business and your economic system means you can't just work in isolation, and that's why I think the point about affecting policy is the most critical piece to this. As you know, I'm a fairly technical person. It's enjoyable just to sit and do my own technical analysis, but that only if improves buildings one by one. And you need to. This is a really tricky problem, but you need for the policymakers work out how to set some standards that's not crippling economically, at least in the short term, because in the long term it makes much more sense for standards to be higher across the board. And I suppose I should say, I think in the engineering community at least, it seems from people we talked to in New Zealand that there is a widespread, once you get a critical mass of consensus, there's a widespread agreement not to go with high damage systems that rely on a lot of damage to meet the code in an earthquake. And I'm not sure to what extent in New Zealand that's a requirement, or it's just becoming a something unwritten that is agreed amongst engineers and clients that they want to do, that they're not going to specify high damage systems anymore.
Yeah, I think that probably comes back to engineering good practice, even if it's not actually in code. But I think the concern you had was, the domino effect from one building on others. Something obviously that's concerns everyone. I don't see any further questions online, although we still have 20 participants online. But I'm going to just see if we have the gentleman back here. If you could speak up or come close so that everybody online can hear it as well. Sorry, we should have maybe had a Thank you.
Thank you for your presentation, William. Just a quick question. Could you potentially speak a little bit to retrofitting some historic structures and what some of the most economical approaches would be?
Mm-hmm. Yeah, sure. I so thought about that as I was putting this together, but I just thought there's a limit to how much I should put in, and I'm not an expert on at least Canadian historical structures. I've worked extensively on that one collection of buildings in Hong Kong, but that was with no consideration seismically. In my experience in Canada has been on the National Arts Centre. We both retrofitted and expanded, and that was a 1960s building, heavy concrete, and we found it to be at around about 75% of current code, which is not bad for a building of that era. The improvements we had to make were basically not to improve that overall level, because that becomes very difficult to do at any reasonable cost. But there is a lot of improvement you can do on the structural side with basically tying things together. We improved diaphragm connections to walls, for example, and for strengthening the gravity systems. So a key part of our design, even for new buildings, is making sure that yes, the lateral system is ductile and it can go wherever it wants, but you really need to make sure the gravity system, the columns, and floor systems just can at least stay there and go with the movement. So strengthening connections to the gravity system, both one piece to another, like column to beam or whatever, as well as back to the lateral system with drag struts, is where you can really make a lot of difference in performance without spending a lot of money on the lateral system itself. And you just accept that it's a 75% of current code, and that means that instead of a 2% in 50-year earthquake, which is the current level for a new building, you're going to be only able to resist something that happens with a 3% in 50-year chance, for example, and it's just that acceptance. It's a different probability level. And then the other thing with existing buildings would be to go and look at how you can restrain non-structural components, mechanical systems and electrical and plumbing, and try to prevent them coming off their supports or undergoing damage, and that will, is a cheaper way of saving yourself money and improving performance in an earthquake. So we did that at the National Arts Centre. As I said, a very large monolithic concrete building. And currently we're working in, well, other people in my office have done a lot on schools here and facing those same, dealing, on those same concepts I just talked about. But we are also currently working with the City of Vancouver to try to create, try to inform them on a policy for dealing with existing buildings. And so we are putting together sample retrofits, the different types of buildings that are around Vancouver, so that the city can then go away and think on the policy side, what level do they say is mandatory that you upgrade to some level, and what level do you say it's, we suggest you upgrade to some level, because there's a large, collection of buildings from the pre-1990s in Vancouver, and I imagine elsewhere in seismic regions in the country that were designed before the 1990 codes. So that's trying to deal with it at a policy level. Yeah.
Okay, thank you, William. I was just checking that there's no more questions online, but we've got content here. Sorry. Do you want to speak up?
Sure, yeah.
Just so that William can hear.
Can you hear me from here, William?
I can just, yes, thanks.
So I'm just wondering, it was very interesting to see those new technologies like tectonus or the slip friction joints and base isolators. But I'm just wondering, do you think it's rational to keep using the same dynamic modification factors after using those kind of technologies, those factors that are currently imposed by a lot of design codes?
If you're referring to for other systems, that the higher,
Like,
yeah.
if you're using like a frame system, it's 8.5, a shear wall is 6, or sorry, it's 4.5, like those numbers. Just
Yeah.
really distribution of the shear forces among the floors.
Yeah, exactly. I mean, this is the point I was sort of mentioning about what I understand is happening in New Zealand, that here we design most other than short concrete buildings, we designed them for IDRO of 3.5, 1.6. So it meaning around about 1/5 of the elastic base shear. So the amount that the building would want to attract, amount of load it would attract in an earthquake, if it was not damaged, we only give it 20% and expect it to move the rest of the motion through damage. And but it's very hard, particularly with, I mean, it's very hard, particularly with private clients, to improve on that, because has direct impact on cost. And I think the position we're kind of taking, or the tack we're taking, is to try to get that through, at least in through public clients, and sort of educate there, because we don't ultimately we can't control what the decisions made by the private clients, but yeah, that's what we would be wanting to do, is to limit that those high damage systems.
Thank you.
Thank you, William. I have seen a question. Alan raised his hand. Okay. I'm just going to try and get the attendance for everybody here, so we're just passing the attendance sheet around. Is there any final question from the floor here? Let me just check online. No questions. Okay, well, William, I'd like to just on behalf of the various group of chartered engineers, thank you very much for a very informative talk on a topic that is definitely very relevant in places, as you point out, in Canada, on the West Coast. So I would like to mention that in lieu of any kind of gift to yourself, our group actually donates some funds to Operation Eyesight in the name of the presenter. So I wanted just to let you know that, and we'll be contacting you just to make sure we know where you want that.
Mm-hmm. That's wonderful. Thank you.
So, well, again, thank you very much for the presentation, and I'd like to just thank everybody online and here for coming out to the presentation this evening. Thank you very much.
Thank you, Hugh. Thank you, everyone, for listening. Thanks.
Thank you.